So I know though that entropy, the second law of thermodynamics, does play a big role here. And I'll ask you, David, I mean, what this role is.
An enormous amount about the way we reason about the world, okay? About the way we make inferences about the past based on records or testimony or other kinds of evidence. An enormous amount about the way we reason about the world depends on a hypothesis to the effect that the entropy of the universe was once much, much lower than it is now. And the reason that this comes up in connection with discussions of fine tuning is that these low entropy is that if you pick at random, where random means where random has a particular kind of mathematical definition. If you pick at random among among physically possible exact microstates of the world, low entropy states are ones that it is much, much less probable that a randomly chosen state would be among. Okay. Low entropy states correspond to a much smaller number of the possible physical microstates of the world than high entropy states do. Moreover, if you do a sort of naive calculation, consider the present macroscopic state of the universe. Okay. Consider all of the possible microstates that are compatible with that macroscopic state. Then use what we think we know about the deterministic equations of motion, okay, to evolve the states that are compatible with the present macro state of the world forwards and backwards in time. If you did that kind of naive calculation, the result would be that states a long time ago are overwhelmingly more likely to be high entropy states than low entropy states. But if that were the case, all of our normal reasoning about what the laws of physics are, about what experiments were actually done on the basis of which we believe these laws of physics, so on and so forth, all of those would fall apart. All of our normal reasoning about the world would fall apart. So the whole structure of the way we reason about the world, the way we investigate the world, seems to take it for granted that we can depend on the claim that the entropy of the universe a long time ago was very, very low. Okay? That is, the universe was in a state which by these normal canons of reasoning counts as very, very rare, very, very finely tuned, very, very improbable if you were just picking a state at random. Okay? So this is an example of what people call fine-tuning problems of this kind.
Well, I guess starting from the beginning and digging in a bit deeper, what do the low entropic initial stages of the universe look like? I'm just trying to get a better sense of how you visualize them in a way that makes their highly ordered status obvious. Does that question make sense?
Yeah, they're very concentrated. They're all the material in the universe is concentrated in a very small region. Okay, that's the crudest and most obvious thing to say. If you have a gas in a box, okay, consider the following three possible macro states of the gas in the box. In macro state one, the gas is all concentrated in a small region around the left-hand corner of the box. In macro state number two, the gas is all concentrated in a small region around the right-hand corner of the box. And in macro state number three, the gas is uniformly distributed throughout the box. The pressure throughout the box is uniform. The density throughout the box is uniform, so on. We have a really sort of tremendously important demonstration from Boltzmann from about 130 or 40 years ago, to the effect that the number of microstates, the number of exact microstates that's compatible with this macrostate that's uniformly spread out throughout the box is much, much, much larger than the number of microstates that are compatible with either of the macrostates in which the gas is more concentrated. Okay, so as a sort of zeroth approximation, situations in which the mass you're talking about is all concentrated in one region. I mean, of course, with general relativity, talk about spatial regions is terribly naive here in all kinds of ways that have to be corrected and blah, blah, blah. But just forget about that for the moment. We're doing a zeroth approximation here. Yeah, concentrated clumps of material, okay, correspond to much smaller numbers of possible microstates than uniformly spread out swaths of material. So that's the kind of thing we're talking about. The sort of state that one is used to associating with the Big Bang or with moments just after the Big Bang, everything stuffed into a small region, stuff like that.
I think I don't like this analogy very much. I mean, I get where it's coming from, but I think that it might be misleading in important ways, because gravity is really, really important here. I mean, it's true that general relativity is the right way to think about gravity, but even in Newtonian gravity, you could say similar things. When gravity is important, when the self-gravity of the objects in your box is important, a uniformly spread out gas is not the highest entropy situation. And in particular, the way that I would put it is, the thing about the Big Bang or the early universe that makes it low entropy is not that it's compact and dense, but that it's smooth. That is the weird thing with all of this gravity. And yeah, I think we agree on it. It's just a matter of choosing your right analogy. But the way that I like to highlight it is, as many other people have said, if you imagine a collapsing universe without fine-tuning so that the future state is special in any way, you could imagine a collapsing universe and all the current galaxies and photons, etc., would smush into a very small region, but it would be wildly inhomogeneous. It would be very lumpy. There'd be black holes in some places and empty space in other places, and that would be a high entropy state compared to the smooth state. And it's even trickier than that, because the really high entropy state, even with gravity, is smooth. So gravity has this weird feature that when things are dense, that's when the local gravitational field becomes important. And under those circumstances, high entropy is not smooth. But as you know, from the Big Bang, the universe expands, right? And it dilutes. And if we're on the right track cosmologically right now, it might very well just keep expanding forever and become smooth again. But that will be a high entropy state in the future. So when you have gravity, you have this very complicated picture when high entropy, when it was dense, would have been lumpy, but it was smooth. High entropy, when it's very dilute in the future, is in fact smooth, just like you might expect.
So
I completely agree.
Okay. So, Sean, at this point, do you have a preferred way of accounting for the fine-tuning, apparent fine-tuning of the universe, or not really?
Well, you have to be a little bit careful because there are many different fine-tunings, and the low entropy of the early universe is one of them, and that's what we're talking about. And by the way, I think David and I will both agree, it is a scandal that modern cosmologists don't care about this puzzle as much as they should. Many of them don't even know.
Susskind does, right?
Some of them do.
Okay.
But there's a majority that don't. I think the number that do is increasing. I think that we're on the right track. But I think that given my various commitments to things, I can see two ways of getting a potentially natural low entropy early universe. One is pretty much the scenario that Jennifer Chen and I proposed almost 20 years ago now, where, like I said, if our universe expands and empties out, it will become a high entropy state and empty with nothing but vacuum energy, the cosmological constant in it. But if you can have quantum gravitational fluctuations in that scenario that pinch off an entirely new bubble of space that then grows into its own universe, that would be a way that this universe could increase in entropy even beyond the empty, what we call de Sitter space, the universe with nothing but vacuum energy in it. And so what you would have is a multiverse where, as you go into the future, you empty out, there's nothing going on, but there's a little quantum bubble that pinches off a little region of space that itself starts in a relatively low entropy configuration, but one with zero energy, zero angular momentum, zero electric charge. And then it explodes into, via inflation, a universe much like ours. So we could have arisen from a baby universe that just was a quantum fluctuation away from a quiescent parent universe. And the cool thing about the scenario is that if you run backward in time, the same thing would happen, but backward in time. Our universe was a baby universe coming out of a parent, but if you go far enough back, there were baby universes coming out backward in time. And so they would think that we live in their past. And so that's the scenario where time is eternal. There's no maximum entropy configuration of the universe. So as time goes on, entropy increases both to the far past and to the far future. The trick of that is having the way that entropy increases be to make universes like ours. That is the diciest part of that story. The other possible way that I can imagine it is if you don't believe that time is fundamental. The thing about the Schrodinger equation of quantum mechanics is there's no singularities or ends of time in the Schrodinger equation. Time is necessarily eternal as long as you're in an evolving universe at all. T in the Schrodinger equation goes from minus infinity to infinity. So that first scenario just lets that happen, where you can have time going eternally toward the past and the future. But there's a whole bunch of people who say, look, maybe time is not fundamental. Maybe the Schrodinger equation is only an approximation that is useful in certain emergent situations. In that case, you could imagine that if time is emergent rather than fundamental, and the space of quantum states, the Hilbert space of the universe, is finite dimensional, then this emergent time will only have a finite number of ticks on the emergent clock. So rather than time going from minus infinity to infinity, it goes from 0 to n, where n is some very large number. And then I can imagine that there's some extra law of physics that says at time equals 0, in this finite lifespan universe, the entropy was very low. I don't know what that extra law would be. I don't know why it would be there, et cetera. That's why I consider this a little bit less promising than the other way. But I think it's logically consistent with the idea that we are obeying the rules of quantum mechanics, but we start with a low entropy condition. So the way that I'd like to put the scenario that Jennifer Chen and I proposed is, to me, it is definitely the best scenario on the market, and it's a really bad scenario because I don't think that we understand the underlying physics well enough right now.
Let me just say one thing. And I'm very much of a fan of both of the lines of thought that Sean was just talking about. So both of the lines of thought that Sean was describing, I think, are very exciting lines of thought that very much deserve to be pursued. There's one thing to say a little further back in this discussion, which was as follows. When I was describing why people thought there's a problem about fine-tuning in the entropy case, okay, I said, look, on what I was calling a naive way of assigning probabilities to macrostates, the macrostates associated with very low entropy are associated with very small probabilities. And this prima facie looks like it's a problem, okay? looks like it's something that has to be addressed, looks like it's some kind of an emergency. But it also ought to be the case that whenever anybody tells you, oh my God, we've got a problem here because we've discovered that the actual situation of the universe as it presents itself to us is enormously unlikely, you ought to immediately take a step back, okay, and say, gee, that's a puzzle. How did you conclude that? It must be that you have intuitions about what's likely and what's not likely, then whose sources are something other than looking around at the actual universe which we find ourselves in, okay? And the first thing you ought to be saying is, where the hell did you get that? Okay. What other sources does this have to do with divine revelation? Does this have to do with some a priori reasoning about what's more and less probable? So the minute you hear something like that, you ought to be very skeptical. Okay. So it's my own view. And this connects with what Sean was saying at the end. If it turns out to be one of the fundamental laws of physics that we simply have to posit, okay, that the entropy of the universe was initially very low. And if somebody says, why did you posit this? The answer is because this gives us a probability distribution to which the world we see is a good fit, okay? The idea that you were once expecting an answer that somehow starts farther back than that is a little crazy, okay? Mind you, if Sean in his first proposal, in this baby universes proposal, has a way to avoid positing such a law, that's great, okay? I got no problem with that. Explanation should go, the deeper explanations go, the happier everybody ought to be, okay? But the idea, which is very widespread, I believe, in cosmology still, that there's some kind of crisis because we're faced with some situation where people think it makes sense to say, hey, here's what I'm worried about. The universe as it presents itself to us is highly improbable, is highly unlikely. The first thing that everybody ought to be saying is, that's a funny thing to say. It must be that you're getting your ideas about what's likely and what isn't from something in some other way than looking around at what happens in the world, okay? That you think you have some a priori idea about what's likely and what isn't, or you have some divinely revealed idea of what's likely and what isn't. You have something other than an empirically founded idea about what's likely and what isn't. And there's a lot to say about this, and I don't want to get into it too much, but everybody's first reaction ought to be, that's funny. Where'd you get that? Okay. And this bleeds a little bit into the conversation that Sean and I were having before about self-locating probabilities, because in the case of self-locating probabilities, there is an idea that you can get from a physical situation, I'm Kirk standing on the surface of the planet, by purely a priori reasoning to some assignment of probabilities, okay? And this has to do with why I was asking what frequency I need to measure in order to determine these probabilities and so on and so forth. I guess I come to these discussions with a very strong prejudice against other than empirical sources for saying the probability is this or the probability is that. And I think this has played a particularly destructive role in fine-tuning. Like I say, if Sean's, if Sean and his collaborator scheme works out about the formation of baby universes, making low entropy initial states more likely, that's fantastic. I think that's a great advance in our reasoning. That's quite different from, just as if somebody discovers something more fundamental than the Schrodinger equation or more fundamental than general relativity, from which either or both of those can be derived, that's going to be a fantastic advance in our understanding. But of course, it's possible that the Schrodinger equation or some relativistic field theoretic generalization of the Schrodinger equation is going to be a fundamental law of nature. And that's going to be fine too. And it might be a fundamental law of nature that the initial probability distribution is such and such. And for somebody to come and object, but that's highly unlikely, I'm just repeating myself here, I think always has to be greeted, at least at first, with some kind of puzzlement as to where these people are getting their ideas about what the probabilities are.
I kind of want to like half agree with David here, and then and half push a little bit beyond, because I'm overall sympathetic with what you just said, but I think it's the thing is that physicists are often very sloppy in not only what they believe, but how they justify what they believe, right? And sometimes that sloppiness,
by the way, I'm dealing with my dog again. Sorry.
Okay. Sometimes that sloppiness is, innocent and forgivable, and we can fix it. Sometimes it's really hiding something that is problematic. In the case of the fine-tunedness of the initial conditions of the universe, it's a little bit unfair to just say it's completely non-empirical. After all, we think there are laws of physics. If we were just talking classical mechanics to keep our life easy, there is a measure given to us by the dynamics, uniquely a measure that is preserved by the dynamics. And the statement is that in that measure, the initial conditions we need for the universe would be very unlikely. And so therefore, physicists say the universe is very unlikely. They don't mean that. They mean that obviously the state of the universe is evidence that the early universe was not chosen randomly from that condition. Therefore, what? Therefore, there's some work to be done. And I completely agree with David that maybe the work to be done 1,000 years from now will turn out to be, yep, that was just the initial conditions of the universe. I guess we learned that. But as a working cosmologist, you want to also say, maybe it's a clue to some physical mechanism that makes it that way. So I think that even though they talk sloppily, it's hiding a pretty reasonable thought process underneath. The problem to me comes when they very blithely extend the same thought process not to the initial conditions of the universe, but to the physical parameters governing the laws of physics, like the vacuum energy or the mass of the Higgs boson or so on. There, we do not have some pre-existing theory that gives us a measure on the space of anything. All we're saying is that, I kind of like numbers that are order 1. I don't like numbers that are of order 10 to the minus 100, and that's basically it. Maybe you can try to do better, but we don't. And just to make this as vivid as I can, because I'm very much thinking about this right now, a huge motivation for building the Large Hadron Collider in Geneva was we think that the value of the Higgs boson mass is unnatural. It is 15 orders of magnitude lower than the Planck scale. And we invented many, many theories to explain why that would be the case in some natural way. And essentially all those theories predicted that the Large Hadron Collider would not only find the Higgs, but a bunch of other particles. It has not done so yet. So this should be, and the physics community is not quite yet woken up to it, I think, a wake-up call that particular sloppy reasoning didn't do well. And look, we spent $10 billion to build the LHC, and I think that was money well spent because we didn't know, and we are trying to discover things. But I would like to see our reasoning about what is natural and what is unnatural be put on much firmer ground than it actually is right now.
Let me just, so there's a mutual admiration festival going on here. I completely agree with what Sean says. Let me just add one remark. The path from the measure, the Lebesgue measure being preserved by the dynamics, okay, to the Lebesgue measure being the proper measure, over possible initial conditions of the universe is just a non sequitur, logically speaking. Okay. Yes, It's not that this measure came from nowhere. Okay, it's not that it came from liking numbers close to one, as in the case of the natural constants, or something like that. But it didn't come from any place. That is, as a logical matter. Okay, any probability distribution whatsoever over classical initial conditions is perfectly logically compatible with the classical equations of motion. Okay, it's true that the classical equations of motion preserve the Lebesgue measure. Okay, preserve a particular measure.
The Liouville measure, I think you mean,
the
right?
Liouville measure. Sorry, that's interesting. That's a note that's an interesting mathematical feature of these equations. The idea that there's an argument that goes from there to it's likely that the initial conditions were equilibrium conditions or something like that is just not true. Okay. Obviously, any distribution whatsoever, any mathematically definable distribution over initial conditions can then be plugged in to the classical equations of motion and evolved into the future to see what you've got. So yeah, it is something people often say, it doesn't come from nowhere. I agree, it doesn't come from nowhere, but it doesn't come from a logically relevant place either here. It's a true mathematical feature of the classical equations of motion that they preserve this measure. Okay, but that doesn't in any way impinge on the fact that you can combine any probability distribution over initial conditions with these same equations of motion and get yourself, a probability map over trajectories.
But I think this is where we disagree, because I think that, of course, I agree with all the statements you made, but I don't think that they're the point here, because it's not supposed to be some kind of logical deductive argument. It's supposed to be clues to being better physicists. And I think that the clue is, if we did have, on the basis of understanding the dynamics of classical mechanics, some measure, the Liouville measure, and also some coarse graining in that measure, like Boltzmann talks about, if we had found out that the initial conditions that we need to account for the observations and the sensibleness of the universe in which we live were generic or in a high entropy macro state in that measure, we would just say, okay, there's nothing more to be explained. We're not going to spend our time looking for a better theory. But when they look very rare and unlikely in that measure, we say, okay, maybe there is something more to be explained. Maybe there's some extra physics going on.
So there is a little bit of disagreement here. Once again, I'm always in favor of deeper explanations. Okay. If we can go deeper than the Schrodinger equation, that's great. If we can go deeper than the Einstein equation, that's great. Start with something simpler. Start with something more intuitively compelling that leads to those. And that's the spirit of what you and Chen did, it seems to me. But it's quite different to say, suppose somebody says, and this seems to me analogous to what people are doing who think there's really a crisis or there's something that must be, that must come in to save us. If somebody says to you, why F equals ma? Think of all the equations that the world or that the classical world could have obeyed. Okay. Take any reasonable measure. I don't know what it would be on the space of equations that things could have obeyed. Why exactly F equals ma? There's a crisis. This is fantastically unlikely. Okay. I say, no, this is confused. Okay. It's just not right to reason about, say, the likelihood of a certain set of fundamental laws of physics, the a priori likelihood of a certain set of fundamental physics, a certain set of laws of fundamental physics, as opposed to another set of fundamental laws of physics. I don't care what measure you put on the space of possible classical equations of motion. F equals ma, or the principle of least action, is going to be one of a huge set of possibilities. Does this constitute some kind of crisis? Does this show that a deeper explanation is required here? It doesn't seem right to me.
But I think this is exactly my point. F equals ma, we think, doesn't require a deeper explanation because it is very much in line with what we might have expected. If the right answer were F equals m times some coupling constant times a to the power 1.001, then people would be saying, wait a minute, I want to explain that 0.001.
Because
that's something I want to dig into.
I don't understand. I thought this is because 1.001 is not 1.
That would be surprising. That would suggest that it's 1 plus a correction, and that correction comes from somewhere, and I want to try to understand it.
Okay. So we do have a little bit of a disagreement here, I think. Yeah.